All right, let's continue with the derivative. We're going to move a bit away from the first principles and look at a specific function type, which would be the polynomial functions. So remember, polynomial functions, in the function into the variable is x, and it will be raised to a power, so x squared, x cubed, x to the power 4, and so on. The power can also be 1, so x to the power of 1 is actually a linear function, which is also a polynomial. And if you raise also x to the power of 0, that will become 1, which is a constant. So let's summarize this. Let's start with the power of 0. If a function is a constant, so if f of x is equal to c, a given value that is independent of x, so that can be a whole number, fraction, a decimal, the derivative is straight away 0. Okay? If the function is linear, you look at the gradient of it is the gradient, but look at the coefficient of x, the derivative is equal to m. Okay. Now let's look at if you combine functions together. So if a function f is a constant times in another function, the derivative is that constant times the derivative of the function, the second function. Below is an example. F of x is 5 times 5x squared is the same as 5 times x squared. The derivative is therefore 5 times the derivative of x squared. Later, in the next slide, I'll show you that the derivative of x squared is 2x. And then you multiply 5 by 2, that gives you 10x. With a sum and a difference, the derivative is the sum of the derivatives, and for the difference, the derivative is the difference of the derivatives. So just for the sum, if you have x squared plus 2x, you separate it, so you do the derivative of 2x, you do the derivative of x squared. Sorry, I did it backwards. Let me rephrase that. You do the derivative of x squared, then the derivative of 2x, which is 2x and 2, and then you add them together. That summary is from your textbook. I prefer this one. This is the one I came up with. I would have that in your bound reference. So the first derivative is the one with power functions. If you have a function to the power of r, so x to the power of r, and r is a real number, so it can be 0, 1, 2, 3, but it can also be a fraction. The derivative is this one. So you multiply by r, and then the power of x, you just minus 1. Okay? Now that will work with if the power is 0. If the power is 0, when you multiply by 0 the derivative, that gives you 0. Therefore, the derivative of a constant is going to be 0. That's what we saw in the last slide. And if you have a function x to the power of n, that's going to be n times x to the power of n minus 1. That's the derivative. And the rest is from the previous slide. Very similar, but it's a good summary to have in your notes. Okay. Notation. I'll look at the notation a little bit further down. The derivative notation is that little dash. I call it f prime, which is a very compact notation to use when you do your working out in your book. Later on in any sort of text format, you will see that second notation, which is the Leibniz notation. It's equivalent, which is above here. How you read this is also what the CAS calculator use, is d over dx is the derivative in terms of x of that function f of x. Because a variable is not going to be necessarily labeled x, it could be a y, it could be t. The Leibniz notation allows you to be very specific when you find the derivative of a function in terms of a specific variable. If you have no doubt that you would differentiate in terms of x, just use the f prime of x notation, which is what you would use mostly through this exercise. To make sure that you kind of not comfortable with just using x, the examples and some of the questions will use different notation and different variables. First, with this example, pause the video, determine the derivative, and also find the value of the derivative when x is equal to 1. To differentiate, you use the sum or the difference of a function, so you have three terms. You can also use the rule of a function times a constant, which is 3 and 6 or negative 6. You get the derivative. Remember, a derivative of a constant is 0. And you should get the same function for the derivative. You can find the derivative using a CAS calculator. At this stage, I recommend you to practice to do this by hand. Do the working out in your book to get you to practice to find the derivative of a polynomial function and using the rules of a product, the sum, and the difference. Then to find the derivative at a specific value, you substitute and you simplify your expression. Please simplify your values to either a fraction or one single real number. Don't leave an expression open like this. Okay, continuing with this function, find the asking you to find the gradient of the tangent. So direct application to finding the rule of a function in terms similar to mx plus c. First you will differentiate, and then you will use the coordinates, mainly the x coordinates, to determine the gradient. And then we use the pair of coordinates to find the complete rule for that tangent. So before we find the gradient, we differentiate this. That gives us a new rule. So that's the rule of the derivative, which is a function of x, different from f of x. Then to find the gradient at that point, you substitute x by 1. That gives us negative 3, which is the gradient at that given point. Later on, knowing that you have the gradient and both coordinates of a given point, you can determine the rule y equals mx plus c by substituting the coordinates, knowing that m is negative 3, by the way. Different notations. So here, instead of using just x, the function is a function of t. Here now our x is a function of t, and we want to differentiate. So using the Leibniz notation, here we differentiate y in terms of t. Here we differentiate x, which is now a function of t, so we differentiate in terms of t, and then z in terms of x, which is the notation. So pause the video, attempt those derivatives using the different notation. Let's move on. So here are those answers. T squared will become 2t. T cubed and plus t, it's a sum of two functions. So the derivative of t cubed is 3t squared. the derivative of a linear function is the coefficient, which is a 1 in front, so that's 1. Next one, 1/3 of x cubed is x squared, or 3x squared times 1/3. And again, it's a sum of a function, so the second function here, x squared, will become 2x, and you combine them as a sum. So you combine them as a sum, but remember they're unlike terms, so you don't simplify that, you leave them separated, they're different powers. Again, an extension of that, I would pause the video and attempt those questions. All right, for part A, it's a at this stage, as it is a factorized form, the best approach at the moment, you'll find a quicker way in year 12, but this year you will need to expand any factorized form. So when you have a factorized form, you need to expand it to get separate terms. Then you differentiate every term, and then you combine them as a sum. So derivative of x squared is 2x, derivative of 6x is 6, and remember, a derivative of a constant is going to be 0, which account for nothing in the derivative. Again, for part B, I know it's a little bit tedious at the moment, is for you to practice expanding expressions. So first expand your perfect square, which is this one, and then you need to expand term for term, which you end up with, you have 3 times 2, you get 6 terms. Combine the like terms, that gives you 4 terms, and differentiate every single one to get the final derivative. Part C, a fraction, separate the fraction, so x squared divided by x is x, 3x over x is 3, and that's a simple linear function. The derivative of x is 1, derivative of 3 is 0. Next one, again a little bit of practice. Here's the derivative, so I'll just continue without any comment. Okay, now here we want to find the gradient at a, hang on, let me rephrase that. So you have a rule, they will give you the gradient, and you need to find the coordinates at which you get that gradient. So the coordinates of that point, the point has to be on the curve. So if it is on the curve, the x coordinate will be, when you substitute into here, you can find from the rule the y coordinate of the point on the curve. So what you need to do for every single one of them, they give you the gradient as a value. So let's do the first one. You differentiate your function, which gives you a rule, the derivative is 3x squared. You want that derivative to be equal to a value of 8, and you're going to solve for x. So here it's a quadratic equation that you solve for x. That will give you two values. Simplify your surds, and to find the point, so we have the x coordinates, you substitute into your rule x cubed, so the y rule. As you substitute those respective values, the negative and the positive, so the positive here gives you the y coordinate, and the negative here will give you the positive, the respective y. Okay. Next one, again you differentiate, that's a linear function, so that's 2x minus 4. You want the gradient to be equal 0, so that gives you a single x value. You substitute that x value into the y rule, and that will give you the y coordinate negative 2. So the answer is 2, negative 2. Part C is 4 minus x cubed. You differentiate, that gives you a quadratic, which gives you two x possibilities, negative root 2 and positive root 2. You substitute into the y rule, that will give you two possible y coordinates, and you get 2 points on the curve. And yes, to confirm, that's it, the end of 17b, and I'll see you in